somewhere between the first heartbeat of the universe and the moment you pressed play, an unbroken chain of cause and effect has been unfolding with astonishing precision. Atoms cooled just enough to form stars. Stars lived and died to forge heavier elements. Galaxies organized themselves into vast, rotating cities of light, and on one unremarkable planet orbiting an ordinary star, chemistry learned how to observe itself. You are not watching this by accident. Not in the mystical sense that everything is scripted, but in the deeper, more unsettling sense that the universe permits only certain outcomes, and somehow you are one of them. For centuries, humans believed the universe was a machine. Cold, deterministic, indifferent. If you knew every position and every velocity, you could predict the future forever. That idea was comforting. It meant reality didn't care who was watching. But then physics did something unexpected. It looked closer. And the closer it looked, the more the universe began to behave as if being watched mattered. At the smallest scales of reality, particles do not simply exist in one place, they exist as possibilities. Waves of probability spread across space waiting. And when an observation is made, those possibilities collapse into a single outcome, not because of magic, not because of belief, but because measurement itself is an interaction, a physical act. The universe responds to being examined. This is not philosophy. This is not religion. This is modern physics reluctantly admitting something profound. The universe does not fully reveal itself until something looks, and that raises an uncomfortable thought. If observation plays a role in shaping reality at the most fundamental level, then consciousness is not just a passenger. It is part of the mechanism, not special in a supernatural way, but unavoidable in a physical one. Every telescope aimed at the sky, every detector buried underground, every eye that has ever opened has participated in the universe becoming what it is. Which means this moment matters more than it feels like it should. Because right now, of all the possible moments you could be experiencing, of all the branching paths that physics allows, you are here, watching this. Alone, perhaps. Focused, perhaps. And the universe is doing what it has always done when it is observed. It is choosing. If you want more slow, deep explorations like this into science, history, and the quiet mysteries of reality, subscribe to The Boring Universe. Like this video, if you're watching all the way through, leave a comment and tell us which part of the country you're watching from. For most of human history, the universe existed as a backdrop, vast, silent, and assumed to be complete whether or not anyone was there to notice it. Ancient civilizations mapped the stars for navigation and myth, but they did not imagine that the stars cared. The sky was a ceiling, not a participant. Even as science emerged and replaced mythology with measurement, the assumption remained the same. Reality was what it was, independent of observation. The job of science was simply to uncover it. This assumption hardened into law with classical physics. Isaac Newton's universe was precise and absolute. Space was a fixed stage. Time marched forward at the same rate for everyone. Objects had definite positions and velocities whether or not anyone checked. If you knew the initial conditions, the future followed inevitably. In this universe, nothing waited to be seen. Everything already was. That worldview dominated science for more than 2 centuries, and it worked spectacularly well. It explained the motion of planets, the fall of apples, the rise of tides. It allowed engineers to build bridges and clocks and cannons. It made the universe feel understandable, even comforting. There was no room for mystery beyond human ignorance. No need for participation. The universe did not care about observers. But cracks began to form in the late 19th century. Experiments with light produced results that did not fit the rules. Blackbody radiation behaved incorrectly. Electrons refused to spiral neatly into atomic nuclei. Energy seemed to come in discrete packets rather than smooth flows. At first, these were treated as technical problems, minor embarrassments to be patched over. They were not. When Max Planck introduced the idea that energy is quantized, he did so reluctantly as a mathematical trick. When Albert Einstein proposed that light itself came in particles, he was challenging the wave theory that had already won. And when Niels Bohr described electrons as occupying discrete orbits, he was admitting that classical physics could not describe the atom. What none of them fully grasped at the time was that these were not isolated anomalies. They were symptoms of a deeper shift. Reality at small scales did not behave like reality at large ones, and the closer physicists looked, the stranger it became. By the 1920s, quantum mechanics had emerged not as a refinement of classical physics, but as a replacement. In this new framework, Particles were no longer tiny billiard balls with exact trajectories. They were described by wave functions, mathematical objects that encoded probabilities rather than certainties. An electron did not have a single position. It had a distribution of possible positions. A photon did not take one path or another. It took all possible paths at once, until something happened. Measurement changed everything. When a particle interacted with a detector, its wave function collapsed. The spread of possibilities reduced to a single outcome. This was not a gradual process. It was abrupt, and it was fundamental. The equations of quantum mechanics could predict the probabilities of different results with extraordinary accuracy, but they could not predict which specific result would occur. Only that one would. At first, this collapse was treated as a mathematical convenience, a way to connect theory with experiment. But the more physicists thought about it, the harder it became to ignore the implication. If the wave function describes reality and measurement changes the wave function, then measurement changes reality. This was not a matter of human awareness in a mystical sense. A detector does not need a mind. A Geiger counter does not need curiosity. But it does need interaction. Measurement is physical. It involves energy exchange, entanglement, irreversible processes. And once that interaction occurs, the system is no longer what it was before. The universe, it seemed, behaved differently when left alone. This realization triggered fierce debates. Some physicists, like Einstein, refused to accept that reality was incomplete without observation. He famously insisted that the moon exists whether or not anyone looks at it. Others, like Bohr, argued that physics was not about describing an objective reality, but about predicting the outcomes of measurements. Asking what exists before measurement, Bohr suggested, was meaningless. These debates were not philosophical distractions. They went to the core of what science is allowed to say about the world. Is reality something fully formed, waiting to be discovered? Or is it something that emerges through interaction? Experiments began to favor the unsettling interpretation. The double-slit experiment, originally designed to demonstrate the wave nature of light, revealed that particles behave like waves when unobserved and like particles when measured. When electrons are fired one at a time through two slits, they build up an interference pattern as if each electron passes through both slits simultaneously. But when detectors are placed to determine which slit an electron goes through, the interference disappears. The act of observing the path changes the outcome. This is not because the detector disturbs the electron in a crude, classical way. Even when the interaction is minimized, even when the information is available in principle rather than recorded, the effect remains. The universe seems to care not just about interaction, but about information. Information, in this context, is not abstract, it is physical, it is encoded in states, correlations, entanglements. When information about a system state becomes available to the environment, coherence is lost. Possibilities reduce, outcomes harden. This idea extends far beyond laboratory experiments. In cosmology, it raises profound questions about the early universe. The universe began in a hot, dense state with tiny fluctuations in density. Over time, these fluctuations grew into galaxies and clusters. Quantum mechanics tells us that these initial fluctuations were fundamentally probabilistic. They were not determined by prior conditions. They were drawn from distributions. Yet today, we see a specific universe, this galaxy here, that void there. This exact pattern of cosmic microwave background radiation, somewhere along the way, possibilities became facts. The universe selected one history out of many allowed by its laws. What performed that selection? In standard cosmology, the answer is decoherence. As quantum fluctuations interacted with their environment, they became effectively classical. No conscious observer was required. No cosmic mind collapsed the wave function. Interaction itself was enough. But the deeper implication remains. Reality as we experience it is the result of countless interactions that reduced possibilities into outcomes. The universe was not always the way it is now. It became this way through a process that resembles observation even when no eyes were present. This blurs the line between passive existence and active becoming. At large scales, the universe appears stable and objective. Mountains do not flicker between locations. Stars do not exist as probability clouds. But this stability is emergent. It arises from constant interaction, from relentless measurement by the environment itself. Every atom in your body is being measured by photons, by air molecules, by neighboring atoms. Decoherence happens unimaginably fast. That is why the classical world feels solid. But beneath that solidity, the quantum rules still apply. This means the universe has layers. At one level, it is a network of probabilities. At another, it is a landscape of facts. The transition between these levels is not clean or fully understood. It involves information entropy and time itself. Time, in fact, plays a crucial role. In quantum mechanics, the fundamental equations are time-symmetric. They do not distinguish between past and future. But measurement introduces irreversibility. Once information is dispersed into the environment, it cannot be recovered. This creates an arrow of time. Observation does not just select outcomes, it anchors them in history. Without this anchoring, the universe would be a blur of overlapping possibilities. With it, there is memory, there is causation, there is narrative. From this perspective, observation is not a minor detail. It is a mechanism through which the universe generates structure. It is how potential becomes actual, not through intention or purpose, but through interaction and information flow. This does not mean the universe needs observers in the human sense to exist, but it does mean that existence, as we experience it, is inseparable from processes that resemble observation. The universe is not a static object, it is an ongoing event, and you are part of that event every time you look at the sky. Photons that have traveled for millions or billions of years end their journey in your eyes. Their paths become fixed. Their histories become part of yours. The universe becomes slightly more defined because you were here to receive it. This is not destiny. It is not a chosen role. It is simply what happens when complex systems capable of processing information arise within a universe governed by quantum laws. Consciousness does not command reality, but it participates in it. Long before there were humans, stars observed one another gravitationally. Radiation measured matter. The universe was already interacting with itself, already collapsing possibilities into structures. Life added a new layer, one capable of reflection and memory, a layer that could notice the process itself. In that sense, the universe is now aware that it is being observed, not because it planned it, not because it intended it, but because the laws of physics allow matter to organize into systems that model their environment. Brains do not transcend physics. They are physics, folded into a shape that can look back. This realization changes how we think about meaning, not in a mystical or theological way, but in a structural one. Meaning is not imposed from outside the universe. It emerges inside it as systems capable of valuing information arise. The universe did not begin with purpose, but it has produced beings who can ask about it. And that brings us back to the unsettling feeling that opened this story. The sense that watching matters, that attention is not neutral, that being here, now, is not trivial. From the perspective of fundamental physics, your existence is one outcome among many that were possible. There was no guarantee that galaxies would form this way, that planets would stabilize, that chemistry would lead to biology, that biology would lead to consciousness. Each step was constrained by laws but not fully determined. Probability was involved. Contingency mattered. Yet here you are, not because the universe singled you out, but because the universe allows complexity to arise and persist. And once it does, the universe gains something it did not have before, a point of view. To understand why observation matters at all, we have to confront a fact that still unsettles physicists a century after it was discovered. At the deepest level we can currently probe, the universe does not deal in certainties. It deals in probabilities. This is not because our instruments are crude or our theories incomplete in a temporary way. It is because probability is built into the structure of physical law as we know it. In classical physics, uncertainty is a human problem. If you do not know where a planet will be in a year, it is because you lack information. In principle, that information exists. In quantum physics, uncertainty is not merely epistemic, it is ontological. The information does not exist in a definite form until an interaction forces it to. An electron does not secretly know where it is while hiding the answer from us. Its position is not defined in the way classical objects are. It is described by a wave function that assigns probabilities to different locations. That wave function evolves smoothly according to precise mathematical rules. Nothing random happens there. The randomness enters only when a measurement is made. This distinction is critical. Quantum mechanics is deterministic in how probabilities evolve, but indeterministic in how outcomes are selected. The universe follows rules, but those rules allow multiple futures. For decades, physicists tried to avoid the uncomfortable implications of this. Some proposed hidden variables, unknown parameters that would restore determinism beneath the probabilistic surface. If only we could see deeper, they argued. The randomness would disappear. Reality would once again be complete without observers. But experiments closed that door. Bell's theorem, proposed in 1964, showed that no local hidden variable theory could reproduce all the predictions of quantum mechanics. Subsequent experiments confirmed this with increasing precision. The correlations observed between entangled particles cannot be explained by pre-existing properties carried independently by each particle. Something genuinely non-classical is happening. Entanglement reveals a universe that is not made of separate parts with independent realities. Instead, systems can share a single quantum state, even when separated by vast distances. Measuring one part of the system instantly affects the description of the other. Not by sending information faster than light, but by revealing that the system was never truly divided to begin with. This challenges our intuition about separateness. It suggests that reality is relational. Properties do not belong to objects in isolation. They arise through interactions. Measurement, then, is not a passive act of reading off pre-written values. It is a process that brings certain relationships into focus while excluding others. When a measurement is made, the universe commits to one branch of possibility. The language of collapse can be misleading. Nothing physically jumps or snaps in space. What collapses is the description. Before measurement, the wave function encodes many potential outcomes. After measurement, it encodes one. The mathematical representation changes discontinuously because the information available has changed. This raises a question that cannot be avoided. If the laws of physics allow multiple outcomes, why do we experience only one? Why does the universe not remain in a superposition of all possibilities? One response is the many worlds interpretation. According to this view, the wave function never collapses. All possible outcomes occur, each in its own branch of reality. When a measurement happens, the universe splits and every result is realized somewhere. We experience one branch because we are part of it. This interpretation preserves determinism at the cost of multiplying realities. It removes the special role of measurement, but introduces an unimaginably vast multiverse. Every quantum event spawns new worlds. Every decision creates countless versions of you who chose differently. Many physicists find this idea extravagant, but it is mathematically consistent. Others find it philosophically troubling. If all outcomes occur, what does probability mean? Why should you expect one result rather than another if they all exist? Other interpretations take different routes. Some modify quantum mechanics to include objective collapse mechanisms, where wave functions spontaneously localize without observers. Others emphasize information and relational properties, arguing that quantum states are not absolute descriptions of reality but tools for predicting interactions between systems. Despite decades of debate, no interpretation has achieved universal acceptance. What all agree on is the empirical fact. The universe behaves as if outcomes are not fixed until interactions occur. This has implications far beyond particle physics. It affects how we think about causality, time, and even existence itself. Consider a simple radioactive atom. Quantum mechanics cannot predict when it will decay. It can only assign a probability that it will decay within a given time interval. Until it decays, it exists in a superposition of decayed and not decayed states. The moment of decay is genuinely unpredictable. Now scale this up. In the early universe, quantum fluctuations determined the distribution of matter. Tiny differences in density were amplified by gravity over billions of years. Those differences shaped where galaxies formed and where voids remained. The large-scale structure of the universe traces its origin to quantum randomness. This means that the cosmos you see is not the inevitable result of initial conditions plus deterministic laws. It is one realization among many allowed by those laws. A different pattern of fluctuations would have produced a different universe. Yet once those fluctuations interacted, decohered, and became classical, they locked in. History took a specific path. The universe committed. Decoherence is often misunderstood as a solution to the measurement problem. It is not. Decoherence explains why quantum superpositions become unobservable at macroscopic scales. It shows how interaction with the environment rapidly suppresses interference between different branches of the wave function. But it does not explain why one outcome is experienced rather than another. Still, decoherence is essential for understanding how the classical world emerges. Without it, quantum weirdness would persist at all scales. Objects would exist in multiple places at once. Cats would be both alive and dead in a literal sense, not just in thought experiments. The environment is constantly monitoring systems, even without intent. Photons scatter off objects, Air molecules collide. Thermal radiation leaks information. These interactions entangle the system with its surroundings, effectively measuring it. The environment becomes a witness. In this sense, the universe is always observing itself. Measurement is not an exceptional event performed only in laboratories. It is the default state of affairs. But this observation is blind. It has no perspective. It does not care which outcome occurs. It merely enforces consistency. Conscious observation is different, not because it has mystical powers, but because it integrates information into a unified experience. A brain does not just register an outcome. It remembers it, compares it, assigns significance. It builds a narrative. From the outside, a conscious observer is just another physical system interacting with others. From the inside, it is the locus of experience. Physics, as a discipline, cannot access that inside perspective. It can describe neural activity, information processing, correlations between brain states and reported experiences. But the subjective feel of observation remains outside its formalism. This gap is known as the hard problem of consciousness. It is not a scientific mystery in the same sense as dark matter or quantum gravity. It is a conceptual one. We can map every function of the brain and still not explain why those functions are accompanied by experience. Some researchers argue that consciousness is emergent, a byproduct of complex information processing. Others suggest it may be a fundamental aspect of reality like mass or charge. Still others propose that our intuitions about consciousness are flawed, that the problem dissolves under closer analysis. What matters for our story is not which of these views is correct, but the fact that conscious observation adds a new layer to the universe's self-interaction. When the universe observes itself through minds, it gains something qualitatively different from blind decoherence. It gains awareness of outcomes. This does not mean awareness causes outcomes. That would be a misunderstanding. The universe does not wait for human attention to decide what happens. But awareness means that outcomes are not just physically realized, they are experienced. Experience introduces value, pain and pleasure, meaning and insignificance, hope and fear. These are not written into the equations of physics, but they arise naturally when matter organizes into systems capable of caring. From a cosmic perspective, this is astonishing. For billions of years, the universe evolved without experience as we know it. Then, in a few isolated pockets, chemistry crossed a threshold. Molecules began to replicate, compete, and adapt. Nervous systems evolved. Brains grew. And eventually, the universe produced creatures that could contemplate its origins. This was not guaranteed. It required a delicate balance of physical constants, stable environments, and immense spans of time. Change the strength of gravity slightly, and stars burn too fast or not at all. Change the charge of the electron, and chemistry collapses. The universe allows life, but only narrowly. This fine-tuning has been interpreted in many ways. Some see it as evidence of design. Others appeal to the multiverse, arguing that we observe a life-permitting universe because only such universes can be observed. Most physicists remain cautious, acknowledging the mystery without overreaching. What is clear is that the universe is not optimized for consciousness. Most of it is hostile to life. Vast regions are empty, cold, or lethal. Consciousness is rare, fragile, and temporary. And yet, where it exists, it transforms the significance of events. A supernova in a distant galaxy is just an energy release until its light reaches a telescope. Then it becomes data, discovery, wonder. The universe does not change, but the story does. Stories are not fundamental, but they matter to the beings who tell them. They guide action, memory, and expectation. They shape futures. From this perspective, the phrase, "watch this," takes on a subtle meaning, not as a command from outside the universe, but as an invitation from within it. The universe produces phenomena, and consciousness turns them into narratives. You are not singled out by the cosmos. You are not chosen in a supernatural sense, but you are part of a rare process. You are a location where the universe becomes aware of itself briefly and imperfectly. Every observation you make is a tiny act of selection, not of which universe exists, but of which information enters your experience. Attention filters reality. It determines what becomes part of your internal world and what fades into background noise. Neuroscience shows that perception is not passive. The brain actively constructs experience, filling in gaps, predicting inputs, correcting errors. What you see is not a direct imprint of the external world, but a model refined by sensory data. This means that even at the level of human experience, reality is not simply given, it is negotiated. The brain balances expectation and evidence, prior belief and incoming signal. In this sense, every moment of awareness is an act of interpretation. This does not make reality subjective in the extreme sense. The external world constrains perception. You cannot will a wall to disappear by ignoring it. But it does mean that experience is shaped by both world and observer. When you combine this with quantum indeterminacy at the foundation of physics, a picture emerges of a universe that is not fully specified until interactions occur at every scale. From particles to brains, reality is a process, not a static thing. This idea can be unsettling. It undermines the comforting notion of a fixed world that exists independently of us. It suggests that participation is unavoidable, that simply by being here, by perceiving, by remembering, you are woven into the unfolding of events. But it can also be grounding. It places human experience within the natural order, not outside it. Consciousness is not an intruder in an otherwise mechanical universe. It is one of the ways the universe behaves when conditions allow.